Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Optimization in Civil Engineering. In the last few lectures, we discussed about the multivariable optimization problem and the solution process. Particularly when we are discussing about the multivariable optimization problem with equality constraints, we discussed two different methods of solving. One is the direct substitution method and the second was the constraint variation method. In both the methods, we came to a point where we found that if the number of variables increases beyond certain limit or the number of constraints increases beyond certain limit, the solution process becomes quite involving and cumbersome. We also looked into a situation where we found that if we follow one of the methods to solve, then we require higher order derivative to identify or to conclude if the solution is optimum or not. It prompted us to look for some easier method or some alternate method which can be employed to solve multivariable optimization problem with equality constraints. So today we are going to discuss one such method, Lagrange multiplier method. So let's begin with the Lagrange multiplier method. We'll start the Lagrange multiplier method by recapitulating the constraint variation method, as some of the facts or some of the derivations are the extension of the constraint variation method. So let's begin with the constraint variation method, which we discussed in the last class. So in the last class, when we discussed the constraint variation method, we said that as per the necessary condition, the optimum point x star of the unconstrained objective function must satisfy the first order derivative of the objective function, which is going to be equal to 0, and as well as it must satisfy the constraints. In the equality constraint, these are going to be 0 as well. Now if we find that the optimum point of the unconstrained objective function satisfies the first order derivative of the objective function but not the constraint, then we need to find out the point that satisfies the constraint, which is in this case equality constraint, means it should be equal to 0, and this point we are saying it as x cap. As we had indicated in the previous lecture where we discussed about the constraint variation method, that for optimum point the total differential of the objective function should be 0, and if we want to mathematically represent it, it can be represented as this equation, which is going to be equal to 0. Now if we take some variation about the optimum point x star, and if we want to see if the new point, whether it lies within the constraint or not, then we must check the constraint for the new point with the variation, and the constraint should be equal to 0 for this multivariable optimization problem with equality constraint. So in this case, we are indicating the constraints as equal to 0 for the new point, which is some variation about the optimum point x star. Now if we expand this equation using Taylor series, we have shown that the equation will convert into this, which is going to be equal to 0 at the optimum point x star. Now this equation, when we consider it for two variables and one constraint, we could write the equation as shown here. Now in this case, if we want to replace the term dx2 in our first order derivative of the objective function, which for the two variable is going to look like this, then we are going to get this term, and this is supposed to be equal to 0. Now we'll look into, based on this basic understanding, how we can introduce the Lagrange multiplier, the concept of it. So in this case, as I said, we have obtained the equation of this, which is going to be the 0. Then we can reasonably say, or you can define a factor lambda which is equal to negative of del f del x2 del h del x2. So which is coming from del f del x2 and del h del x2. So if we consider this as lambda, then we can easily write this equation in the form of lambda and the other two partial derivatives, and at the optimum point x star, this is going to be equal to 0. Similarly, if we choose to express dx1 in terms of dx2, then we can write the equation as this way. And of course, at the extreme point, we know that the constraint must satisfy the equality nature. So these three equations, which is number 1, number 2 and number 3, eventually becomes the necessary condition for the potential solution of the problem. Now in this expression of lambda, we need to understand the denominator part. In order to obtain a value of lambda, this cannot be 0. It should be a non-zero, then we can obtain a value for the lambda. Similarly, if we are replacing or expressing dx1 in terms of dx2, this term is going to be del h by del x1, and that has to be not equal to 0 at the x star. So these are the conditions which we must follow, or which we must have to find the extreme point, and it should satisfy the condition, but the partial derivative of the constraint with respect to the variable we are choosing. Now let us look into how we can extend this for all the variables and complete optimization equation. So as we had indicated earlier, our optimization equation can look like, where we are minimizing or maximizing an objective function with equality constraint, where x, the capital X, stands for the n-dimensional array, and then if we want to introduce the Lagrange multiplier for the constraint, then we can easily transform the function into this way, so that it satisfies the three necessary conditions we discussed earlier. So in other words, the three necessary conditions we discussed earlier can be commonly generated by reconstructing the optimization problem into the form of this equation. And as you can see in this equation, the problem has converted into an unconstrained optimization problem, and we can use the unconstrained optimization problem characteristic to solve it. So let's see step by step how we can solve this problem. Now in this Lagrange function, we have n unknown x and m unknown lambdas. So for the necessary condition, when we do the partial derivative of the function, the Lagrange function, we can write that function as this way. This particular equation, if you recall, for the two variable will satisfy the first and the second conditions, and we also need to satisfy the equality constraint. So once we do the partial derivative with respect to the lambda values, then we can easily obtain the equality constraint, which was our third necessary condition in the two variable optimization problem with one constraint. Now in these equations, we have n number of equations from this, and we have m number of equation for this. So total we have n plus m equations, and our unknowns are also n plus m. So if we solve this system of equation, we can easily obtain the value of x star and lambda star, and these values are going to give us the potential extreme points for the function where we can obtain the optimum value. However, whether the solution obtained is going to yield maximum or minimum, that needs to be checked using the sufficiency condition. So we'll move to the sufficiency condition, and for the sufficiency condition, we need to do the second order derivative of the Lagrange equation, and if we do the second order derivative of the Lagrange equation, we can write it in this format. And Hancock had shown that this particular equation would be positive or negative definite for all admissible variations of the design variable or the decision variable when all the roots of a polynomial z defined by a determinantal equation is positive or negative respectively. So now we'll look into how we can introduce z in this particular equation and what this sufficiency condition, the second order derivative of the Lagrangian equation, is going to look like. This Lagrangian equation is going to be a matrix of m plus n order, and in this Lagrangian matrix, if we look into the determinantal equation, then we need to see the z values which are here in the diagonal components, and if we try to solve, then we can get the roots of the z. Now in this case, you will find that the z is going to be of n minus mth order polynomial, and any of the Lij can be represented as the second order derivative for the values of optimum x star and the lambda star. Hij is the partial derivative or first order derivative of the constraint with respect to the variables considered at the optimum x star. So we just need to solve the polynomial of the z, and we can easily say whether we have obtained an optimum point or not. Now in this solution, if we find that all the roots of z are positive, then we can say that the optimum point x star is going to yield the minimum function value. If all the roots of z are negative, then the optimum point x star is going to yield maximum function value. In the third case, if some are positive and some are negative, then x star or the optimum point x star is not an extreme point. So with this, let's look into one of the example to understand this problem better. So in this problem, we need to find the dimensions of a cylindrical beam whose surface area is equal to 24 pi and has maximum possible volume. Then let us first assume that the radius of this cylinder is r and the length of the beam is L. So we need to maximize the volume, which can be represented as max of function which is of RL are the design variable, and the equation is going to be pi r square L. So it's a cylinder of length L and radius r. Now we also said that the total surface area is going to be equal to 24 pi. So the total surface area of the two sides are 2 pi r square, and the surface area of the cylinder's side is going to be 2 pi rl, that is equal to 24 pi. Now we have the objective function and the equality constraint. If we want to represent this optimization problem into a Lagrange function, then we can easily write it in this way, where we have the objective function multiplied with lambda. In this case we have one constraint, so it's only lambda, and then the expression for the equality constraint. So that becomes my Lagrange function. So this Lagrange function, we need to first of all do the partial derivative for the necessary conditions, and for the necessary conditions, if we are doing the partial derivative with respect to the first design variable which is r, then we can write it in this format, and this partial derivative is supposed to be equal to 0. The second partial derivative with respect to length, which is my second design variable, is going to be this, and which needs to be equated to 0. And the third partial derivative, which is going to give us the constraint. So if we do the partial derivative with respect to lambda, it is supposed to give us the constraint, and it is going to be this equal to 0. So it satisfies the necessary conditions, equations, and if we try to solve all these three equations, we have three unknown, we can easily solve it and obtain the optimum or extreme point values, where r star is equal to 2, L star is equal to 4, and lambda star is equal to -1. And for all these values, we can easily calculate the function value is going to be 16 pi. However, we cannot conclude at this point that we have obtained the maximum value unless we look into the sufficiency condition. So let's look into the sufficient condition. So we have the design variable value of this, and in the sufficiency condition we need to calculate the various terms of the Lagrange L11, which is the second order derivative, partial derivative with respect to the first variable at this point, and we can easily write this is going to be 4 pi. The second one is going to be the partial derivative of the Lagrange function with respect to first the radius, second with respect to the length, and then once we substitute the value of the optimum or the extreme variable value, we can get the value of this as 2 pi. Now the third one is going to be with respect to the length, the partial derivative with respect to length. Twice if we do, we are going to get 0. And if we look into the constraint h11 and h12, so if you recall the matrix, we can get this value at the extreme design variable value, and we can get the values as 16 pi. Similarly, for the other variable L, we can get the value of 4 pi. Now we need to construct the matrix or for the determinantal equation, and if we do the determinantal equation, we can write L11 was 4 pi minus z, then L12 was 2 pi and H11 was 16 pi. Then we look into the L21, that is going to be 2 pi, L22 was 0, so 0 minus z, and we are looking into H12, that is going to be 4 pi. Then we are looking into H11 again here, which is going to be 6 pi, and this one is going to be H12 again, it's going to be 4 pi, and this is going to be 0. So this determinantal equation, we need to equate it to 0, and if we try to solve, this is what the equation is going to be for the z, and as I had indicated earlier, the z would be of the order of n minus mth polynomial. In this case, n is equal to 2, this is equal to 1, so this is of the first order polynomial, which is this equation, and if we solve z, we obtain this value where this is negative, indicating that my function value is going to be the maximum. So this is how we apply Lagrange multiplier to solve multivariable optimization problem with equality constraints. So in today's lecture, we saw how we can use effectively Lagrange multiplier to convert a multivariable constraint problem into unconstrained multivariable optimization problem, particularly when the constraints are of equality nature. So in the solution process, we also found that we can decide or we can conclude whether a point obtained by the method is going to be optimum or not just from the second order derivative of the Lagrange function. Like the previous two methods, we were not confined to a situation where we couldn't decide whether the point is going to be optimum or not. Now in the optimization problem, you will find that not all the problems are having equality constraints alone. There are problems with inequality constraints. So it is going to be important to see how we can solve the multivariable optimization problems with inequality constraints. Next class, we'll discuss about the multivariable optimization problem with inequality constraints and the solution method. Thank you and see you in the next class.